Is a fabulous review of the stuff that we've been working on in chapter 4. Because in this one section, we're going to go back and look at first derivative test, relative maximums and minimums, increasing, decreasing, points of inflection, concavity, all that stuff that we did in the beginning of the chapter. And then we're also going to look at the horizontal and vertical asymptotes that we were looking at in section 4.4 with those infinite limits and limits at infinity. So we get a really great review of all of that while we look at section 4.5, which is how I can take all that information and apply it to a graph to help me when I have to do graphing by hand. So on page 263, they say, I realized that you could graph anything on the face of the earth if you just plotted enough points. And so there on page 263, they were given an equation that they plotted 12 points for. When was the last time you made an XY chart where you actually took the time to plot 12 points? I mean, surely that is enough, right? They have gone above and beyond. And so they plot those 12 points and they seem to make this beautiful, perfect cubic equation. And so they assume, yeah, that's my graph. And in actuality, you can see what they drew in figure 2 that looked like the cubic equation. In actuality, what you see there in figure 3 is the actual graph. Looks nothing like that at all. So, great. How am I supposed to know when enough points is enough? And how am I supposed to know when my graph is right and when it's not? And besides the fact that that's going to take forever to plot that many points, and it still wasn't good enough. So, those are the drawbacks of the point plotting method that they discuss there on page 263. So instead, what I'd like to do is utilize some of the tools that I've learned over my history and pre-cal and also in the new things that we've picked up in this chapter and see how that could help me with my curve sketching. All right, so to begin with, example number 1, they give me a rational function, just a polynomial divided by a polynomial. Before I start, I want to make sure that that's in lowest terms, that I couldn't take out a greatest common factor or factor it in any way where I'd have something that would cancel, so it would be easier to work with. But once it is in its lowest terms, then they go through and they talk about numerous things that I could consider. Now, if I'm working out a homework problem or a test question, am I going to go through and do A, B, C, D, E, F, G? Probably not. I'm not going to necessarily need every one of those components, but it's nice to know that I have all of these things at my disposal so that I could pick and choose the things that I do need that would help me and utilize those things. So we'll go through all of them today so that we can kind of see which ones would be helpful for us in whatever situation we're working with. First thing they mentioned is it's always a good idea to think about your domain of your function, because there's no need graphing something where it doesn't even exist, right? So your domain is going to be all real numbers unless one of two things happens. What are they? 0 in the denominator. Negative under an even indexed radical like a square root or a fourth root. Don't have a radical here, but I do have a denominator. So I'm going to have to say my denominator can't equal 0. So if my denominator can't equal 0, that means that x can't be positive 1 or negative 1. And if I wanted it in interval notation, I could give that as well. All right, the second thing that they suggest is that I find my x and y intercepts. Now, if we're making an xy chart, those are usually the first points we find anyway. But remember that your x-intercept, you find how? What do you do to find an x-intercept? Set y equal to 0, right, which in this case, if I'm going to set y equal to 0, you're exactly right, that would be where my numerator equals 0, because the only way a fraction can equal 0 is where its numerator equals 0. So you're both right. Yes, it is where y equals 0, and in this case, in our fractional case, it is where the numerator equals 0. All right, how do you find a y-intercept? How do we find a y-intercept? Yeah, set x equal to 0. So I'm literally just going to put 0 in the place of x in my function. So if I plug 0 in for x and see what I come up with, then I end up with 0. Something else that they suggest to me that I might want to consider that is really an often overlooked thing is the idea of symmetry, all right? You might remember we've talked about even and odd functions before. And the way that we test for symmetry with even and odd functions is we put a negative x in the place of x in the function. When I plug negative x in the place of x in a function, if I get the exact same thing that I started with, what type of function is that? Even or odd? Even, right. And an even function is going to be symmetric with respect to what? The y-axis, yes. If I had plugged in negative x and got the exact same, the opposite of what I started with, that's an odd function. Odd functions are symmetric with respect to what? The origin, yes. Those are the ones that you turn them upside down and it's the same picture upside down as it is right side up, right? Now, symmetry is often overlooked, but think about how powerful this is. Because this is an even function, I literally just cut my work in half. Because if this is symmetric with respect to the y-axis, when I figure out what the left-hand side of this graph looks like, I will automatically know what the right-hand side looks like. Yes? Literally cut my work in half. If it's an odd function where I can turn it upside down and have the same thing upside down as I do right side up, also going to cut my work in half because it's going to be symmetric about that origin. Okay? So it's probably worth taking the 15 seconds it would take to check for that for the crazy amount of work it would save me. All right? All right, then asymptotes. We've been talking about horizontal and vertical asymptotes. There are also slant asymptotes that we studied last year. We'll see that a little later on today. We'll review back through that topic again. But for right now, we're focusing just on horizontal and vertical, right? What's the practical way to see where your vertical asymptotes are? Not the formal fancy definition of a vertical asymptote. What's the fast? Yeah, you can look at your domain or you can set the denominator equal to 0, right? Because your domain is going to tell you where your denominator was equal to 0, right? So to find our possible vertical asymptotes, we're going to set that denominator equal to 0. We've already done that up here in the domain. It got positive and negative 1. So that means that I have possible vertical asymptotes at positive 1 and negative 1. Now, if I have to verify those or justify those for AP purposes, remember that the justification or the verification is that the limit as x approaches that value, if I'm saying there's a vertical asymptote at positive 1, then the limit as x approaches positive 1 from either the left or from the right has to go to either infinity or negative infinity. Same story if I'm going to say that I have a limit at I'm going to have a vertical asymptote at negative 1, then the limit as x approaches negative 1 from either the left or from the right has to go to either infinity or negative infinity. I don't have a graphing calculator to throw this into to verify that. That would defeat the whole purpose of what we're doing today, right? I should be able to verify those limits by hand, in my head, using the logic that we were using all the way back in section 2.2. Here's how that logic went. Let's say that we're trying to verify this first one right here. The limit as x approaches 1 for f of x is equal to infinity. All right? If I come back up here to my original function and I say, okay, if I think I have a vertical asymptote at positive 1, then the limit as I approach 1 for this thing is what I need to evaluate. If I plug 1 into this numerator, I'm good. I'd get 2 times 1 squared, so I'd get 2. So the limit in the numerator is fine. The limit in the denominator is not. It's not well behaved, so I'm going to have to get creative. If I plug 1 in here, I'm going to get 0 in the denominator, right? So I could think about, okay, it's probably easier to think of positive values than it is negative, so I'm going to try approaching it from the right-hand side, from the positive side first. So if I were approaching this denominator from the right-hand side of 1, I'd be putting values in like 1.1, 1.01, 1.001, right? So if I took something like 1.1 and squared it and then subtracted 1, it'd be a small number, right? I don't even have to figure out in my head what that value would be or write it out on paper. I just know it'd be a small number. If I did 1.01 squared That's going to be an even tinier value, right? And then I subtract 1 from that, that's going to be an even smaller decimal. If I did 1.001 squared minus 1, that'd be an even tinier decimal. So my numerator is staying the same at 2. It was well behaved. It was fine. My denominator is getting smaller and smaller and smaller. What is the overall fraction doing? Getting bigger and bigger and bigger, right? And so we could say, okay, then it's going to infinity. I have to be able to do that type of logic in my head. We've been doing that since section 2.2 in our head. But that's the only way that I'm going to be able to do a verification without my calculator to look at a graph, okay? And we could do that same type of scenario for the negative one if we wanted to as well. All right, then I need to find horizontal asymptotes. What was the practical, not the definition, but what was the practical way of finding horizontal asymptotes? I can take the limit as x approaches infinity and negative infinity. Yes, that definitely will work. Yeah, look at the degree of the numerator and the denominator. And that way I can literally eyeball it and know what my horizontal asymptote is, right? So if I go through, remember that if the degree of your numerator is larger than the degree of your denominator, you don't have a horizontal asymptote. If the degree of your numerator is smaller than the degree of your denominator, you will have a horizontal asymptote. It will be y equals 0, no questions asked. If the degree of your numerator is equal to the degree of your denominator, as is the case here, then you will have a horizontal asymptote, and it will be leading coefficient of the numerator over leading coefficient of the denominator. So it would be, in this case, 2 over 1. So I can look at it and say, because the degree of the numerator equals the degree of the denominator, I'm going to have a horizontal asymptote, leading coefficient over leading coefficient, it's going to be y equals 2. If I had to justify that or verify that, then yes, I could go back to that idea of the limit as we approach infinity. And when we take the limit of a rational function as we're approaching infinity or negative infinity, what was the cool tool that we used for that? Yeah, divide everything by the highest power of x in the denominator, right? Because when I do that, what I'm left with is typically just constants, and the limit of a constant is that constant, like we have here, the limit of 2 is 2, or a number over a variable, which when you're taking the limit approaching infinity or negative infinity is going to go to 0. So we're able to say the limit of a constant is that constant, the limit of a constant is that constant, the limit of a number divided by a variable is 0, and that gave us a fast way of getting that limit. So if I had to justify this or verify this, I could take the limit as x approaches infinity or negative infinity and show that it gives me this numerical value, and that's my justification for my horizontal asymptote. All right? Then let's go back and think about where our original function might have been increasing and decreasing and where it might have had maximums and minimums. What do I need to help me figure that out? The derivative, right. So I have no doubt that you know how to take the derivative at this point. They do work that out in the textbook if you want to see the work for coming up with a derivative. I just listed the derivative here, okay? So if I want to figure out where my original function was increasing, how does that relate to the derivative? If I want to figure out where my original function was increasing, how does that relate to the derivative? It's where the derivative is positive, right? And where the original function was decreasing? Where the derivative is negative. So I need a sign graph for the derivative, right? I got to figure out where it's positive and negative. So I'm going to go through and make a sign graph. So I got to find my critical numbers. How do I find critical numbers? I told you, fantastic review, right? It's like the whole chapter in one problem. How do I find critical numbers? Set the derivative equal to 0, or look for where the derivative does not exist, right? So if this is my derivative and I want to figure out where does the derivative equal to 0, it's a fraction. So in a fraction, the only place it equals 0 is what? Where the numerator equals 0, right? And where this is not going to exist is where my denominator equals 0, right? So if I'm looking for critical numbers, Where does my derivative equal 0? That's where the numerator equals 0. Where does my derivative not exist? That's where the denominator equals 0. So I'm going to set the numerator and the denominator equal to 0 to find my critical numbers. And I need to pay particular attention if I end up with like a double root or a triple root or anything like that, because remember that makes a difference on my sine graph. So I'm going to make little notes for myself about that as well. All right, so let's make our sine graph then. I know that I have critical numbers at -1, 0, and +1, so I'm going to indicate those on my sine graph. It's also a really good idea to label my sine graph so that I can remember this was the one I made for the first derivative. If I turn around and make one for the original function or the second derivative as well, then it's helpful to have this one for the first derivative. All right, so how do I figure out where this is positive and negative? What do I need? Test point, yes. So I'm going to use +2. Am I going to plug +2 back into the original or the first derivative? The first derivative, right. If I am looking for a sine graph for the first derivative, I'm looking for where the first derivative is positive or negative, and I'm picking a test point to figure that out, it's got to go back into the first derivative, right? So let's take 2 and plug it into the first derivative, and I get a negative value. So over here at 2, this is negative. What happens when I cross a double root right here at 1? Sign changes twice, so it will appear to not change at all. How about at 0 where I had a single root? Sign changes once, and then over here at -1 I had a double root. It changes twice, so it will appear to not change at all. So there's my sine graph for my first derivative. So looking at that, I can tell where it's increasing and decreasing, right? Okay, so what's going on from -infinity to -1? Increasing. How about from -1 to 0? All right, so increasing from -infinity to -1 and -1 to 0. I do have to leave out that value of -1 because it was neither increasing nor decreasing there. If you remember, the function doesn't even exist there. It's not even in the domain, so can't really say it's increasing or decreasing there. All right, then from 0 to 1, what's it doing? Decreasing. And from 1 to infinity? Decreasing. All right, while I've got my first derivative and my first derivative sine graph, I can use that to help me figure out my maximums and minimums, right? Am I going to have any maximums or minimums? Yes. What am I going to have? A maximum where? At 0. If I had to justify that for AP, what would I say? Here's my sine graph. That's good enough. No. What would I say? Right. So they're not asking me to justify here, but we just want to constantly review that. I would literally have to state my function is positive where x is less than 0, and it's negative where x is greater than 0. Therefore, I have a relative maximum at 0 because the derivative changed from positive to negative. I literally have to state the first derivative test. Even though it's right there on my sine graph, I got to state it. Okay, so I have a relative maximum at 0. That's my x value. How do I find the y value that goes with that? Plug 0 back into the original function, right? If it is a maximum or minimum of the original function, I got to go back to the original, not to the derivative. So I'll go back and plug 0 in, and I get 0. All right, then we can think about concavity in terms of thinking if this is concave upward or concave downward. I'm going to need the second derivative for that. So again, I don't have any doubt that you can create a derivative, so I just wrote it for us there. We again, to go through and find possible points of inflection, we need to set the second derivative equal to 0 and figure out where the second derivative doesn't exist. So second derivative will be equal to 0 where the numerator of that fraction equals 0, and the second derivative will not exist where that denominator is equal to 0. When I set the numerator equal to 0, I get imaginary, so I don't have imaginary possible points of inflection, so I don't have to worry about those. Set the denominator equal to 0, and I do get a couple of values that I can use for my sine graph. All right, so let's make our sine graph. I'm going to put on -1 and +1, and I've made myself a note here that they're triple roots because, of course, that's going to affect my sine graph. Pick a test point. I pick 0. What am I plugging that back into? The original, the first derivative, the second derivative, what? Second derivative. If I'm making a sine graph for the second derivative, I'm plugging the test point into the second derivative. So when I plug 0 into that second derivative, I got a negative value. So I'll come up here to 0, I've got a negative value. What happens when I cross a triple root? The sign changes 3 times, so will it appear to change or not change on my sine graph? Yes, it will appear to change. So we're going to have negative here, positive here, positive here. All right, so what does that second derivative then tell me about concavity? Where the second derivative is positive, my function is concave up. Where the second derivative is negative, my function is concave down. So I could go through and say, okay, concave up from -infinity to -1. Concave up from +1 to infinity. And then concave down from -1 to +1. Anywhere my function changes from concave up to concave down, or where the second derivative changes from positive to negative or negative to positive, I have what? Point of inflection. So it looks like I'm going to have points of inflection at 1 and -1. But if you remember back in the very beginning, 1 and -1 were not in our domain. This function doesn't exist there. I can't have a point of inflection where the thing doesn't exist. If I didn't happen to remember that about my domain, I could go through and plug 1 and -1 back into the original function to find the y value that goes with those x values, and I would get undefined. And so that would remind me, hey, these are not points of inflection because I don't even have values here. Okay, so now that I have this plethora of information, how can that help me with my graphing? All right, let's start at the top. I know that this function isn't going to exist at 1 and -1, and I know I have an x and y intercept at 0, 0, so I'm going to go ahead and plot that right there at 0, 0. I know that this is symmetric to the y-axis, so once I figure out what the left-hand side looks like, I'll also know what the right-hand side looks like, or vice versa. I know that I have horizontal and vertical asymptotes that we've already identified. So I have vertical asymptotes at 1 and -1. And I have a horizontal asymptote at 2. So vertical asymptotes at -1 and +1. Horizontal asymptote at +2. You will have a piece of your graph on both sides of every vertical asymptote. You will have a piece of your graph on both sides of every vertical asymptote. So what happens is I have people come over here and do all of this work to generate this piece of the graph, and then they don't give me anything about this piece or about this piece, and it's frustrating to do all that work and then lose so many points because you only give 1/3 of your graph. Be sure you check both sides of a vertical asymptote. In this case, I will have a piece of the graph here, a piece of the graph here, and a piece of the graph here. There will be 3 pieces to this graph. So let's come over here and let's think about this left-hand piece, right? What do I know about the piece that's less than -1? Well, I know from -infinity to -1, that entire thing is increasing. It's going up. And I know from -infinity to -1 that that whole thing is concave up. So if I sketch that, if something is going up and it's concave up, then that's its shape, right? There's no other shape that can have. If the whole thing's going up and it's concave up, it has to look like that little arc right there. So then I can think about, where could I put that arc on this left-hand piece of the graph? I couldn't put it down here, because if I put it down here, there'd have to be an x-intercept, and there's not one, and it wouldn't approach those asymptotes. So that means it has to be right there. I haven't plotted a single point, and I know exactly what 1/3 of my graph looks like. If it would make me feel better, I could go in and plot a point or two, So, you know, I come over here and say, okay, if the asymptote's at -1, maybe I want to plug in like -2 and -3. I plot those 2 points and it lays out exactly like I thought it would, where, okay, I've got these 2 points right here. I know I have to approach this asymptote. I know I have to approach this asymptote. And sure enough, everything I know about that piece of the graph is working. It's increasing. It's concave upward. There are no x-intercepts. There are no maximums and minimums. All of that is exactly what I've got there. If I caught that part about symmetry before, I also know what this piece of my graph looks like, right? I just got 2 for the price of 1. I would know what 2/3 of my graph looks like, and I haven't plotted a single point yet. All right, but let's go to that middle piece. All right, for my middle piece, let's think about what I know for the piece between -1 and +1. All right, for the piece between -1 and +1, I know that it's increasing from -1 to 0, and it's decreasing from 0 to 1. I know that I have a relative maximum then where it changes from increasing to decreasing, and that maximum is at 0, 0. So here's what I know. I've got to come up to 0, and then I've got to go back down as I go away from it. I also know that from -1 to 1, that whole thing is concave downward. So I could say, okay, if it's got to go increasing and then decreasing, the whole thing be concave downward. That's the shape of that graph. And I know that when it comes to that highest point, it has to be right there at 0, 0. I know exactly what that piece of the graph looks like as well, and I didn't need to plot any points. But if it makes me feel better, I obviously could plot a point. Like I could come over here and plug in -1/2 just to make sure it's doing what it's supposed to do. From that idea of symmetry, I would also know that +1/2 would be doing the same thing. And that would verify for me that I was on target with that. If I hadn't already figured out from symmetry what this piece of the graph was going to look like, I could say, okay, from 1 to infinity, what do I know about this graph? Well, I know from 1 to infinity it's decreasing. And I know from 1 to infinity it's concave upward. So if the whole thing has to be going down and it has to have that concave up shape, that's the only way that arc could look. Where could I draw that? Well, I can't draw it down here because I don't have any x-intercepts and it wouldn't approach those asymptotes. So it has to be up here, approaching those asymptotes. If I wanted to verify, I could plot 1 point just to make myself feel better. Sure enough, it is where I think it's going to be. If I have that point and I know I have to approach that asymptote and I have to approach that asymptote, it also bears out with everything else that I know that there are no x-intercepts there, there are no relative maximums and minimums there, the whole thing is concave upward, and the whole thing is decreasing. So in the book they plotted 12 points and it wasn't enough to get an accurate graph. We really could have gotten by without plotting any points at all, but definitely with 3 points, we've got this covered where we have a pretty much a flawless graph. All right, we mentioned before that idea of slant asymptotes. Let's talk about that for just a second in closing. A slant asymptote is exactly what it sounds like. It's an asymptote that is not horizontal and not vertical. It's slanted. You will only have a slant asymptote when the degree of the numerator is exactly 1 more than the degree of the denominator. Therefore, you can't have a slant asymptote and a horizontal asymptote at the same time, right? For a horizontal asymptote, what happens if the degree of the numerator is larger than the degree of the denominator? There's not one, right? So if you have a horizontal asymptote, you're not going to have a slant. But if you don't have a horizontal asymptote because of the degree of the numerator is larger than the degree of the denominator, you better check and see, is the degree of the numerator exactly 1 more than the degree of the denominator? Because if it is, I'm going to have a slant asymptote. Okay, then how do I find it? I find it by literally dividing that polynomial. So if I take x cubed and I divide it by x squared plus 1, the answer that I get, ignoring my remainder, is what I set equal to y to be my slant asymptote. So when I divide that polynomial, the answer that I get, I'm going to ignore my remainder, literally just toss it out. But I'm going to take that answer and set it equal to y, and that will be my slant asymptote.